Hi everyone, this is our midterm presentation, and our topic is the party algorithm, and this is our member list, and I'm James, and our task distribution is like as below. So it's me and Minh, Alex and PUTU as our team members. And about our presentation, I'll separate in four steps. First one is introduction, and second is algorithm and the practical work, and the last one is what we need to do extend. Okay, let's talk about our background. It's we do is meta heuristic, and some researcher meta heuristic find a solution that is good enough in a computing time that is small enough. Means we need to get a balance of each two requirement, and the other researcher said you are given in a candidate solution to your problem, and you can test it and assess how good it is. About meta heuristic. And the other one special noun we want to mention is psychology, and in the dictionary explanation means a study of mind and behavior in relation to particular field of knowledge or activity. And for the Opport in 1968 is scientific study of how people's thoughts, feeling and behavior. So it's like a behavior of human. And in our algorithm, we separate the people who join the party into two sets. It means two kinds of people. One is extrovert, and the other one is introvert. So in the Cambridge Dictionary, extrovert means energetic person who joins being with other people. And in Sankara's research they get energized in the midst of multiple simultaneous conversations. And the introvert means someone who is shy, quiet, and prefer to spend time alone, by the dictionary explanation. And also in Sankara's research, he said need time for being alone, spending time for individual activities. So it's two different type of people. Okay, let's talk about what enlightened us to think about this algorithm. And this is party. In a party, you will see many kinds of people, and they will have different behavior, and most of the time they will have alcohol or some cocktail or just juice or actually drinks. So that's what enlightened us to think about this. Since we talk about our metaphor for a party, let's talk our former studies to our algorithm. And the first one is PSO, and we take its global and local position concept to update the position of the best global or local in one iteration. And the other formal study is word search algorithm. We use the concept of visual domain because in our we're supposed to let the people in the party can only walk to the place they can see. It's a realistic situation. So in the party model, we will adapt how people will behave in a party. So in a party we have snack, toys or entertainment. And for the objective function that needs to be optimized is associated with the heat intensity and a hotspot in the party. The higher the heat will attract more people, means the better value for our objective function. And also we find the hotspot on what the least vocabulary means on the internet and what is its explanation, and it includes a place of significant danger or violence. So it definitely not happen in party, right? Not for no so much joke. And then we are talking about our model, and we separate two kinds of person that I mentioned before. In a party, that there are like two sets. And the introvert person, we say that like shy guys will try to stay away from the hotspot, because the hotspot is like like an extrovert person, like full of snack or full of entertain things. So the introvert person will try to stay away, and the extrovert will try their best to go to the hotspot with the highest hit. So about the party model, there are another important means that there are of alcohol provided in the party. So some of them get drunk and started to move randomly, like you are in party and many drinks and almost include alcohol, and you have a high probability to get drunk. But yes, so you cannot control yourselves, unfortunately, and sometimes they start to sober again with some condition, and the condition is based on after a period of time, like maybe after 2 hours, but in actually we set the iteration, or when the drunk's position is in a global hotspot, means you go to a hotspot, so you get sober. Okay, let's talk about our pseudocode in the algorithm. And first we generate a step size, means like one human's walking path, and we also generate for the initial part, like others algorithm, we generate random population and generate velocity like PSO. So we started to do we will set the max party time and generate visual radius like a WSA, like wolf do, and we will compute velocity and do the things like PSO. So and the end of we update the hotspot and evaluate. We will randomly create a drunker, means the people include introverts and extroverts. They have rate to get drunk. So let's take a look. So after the pseudocodes, let's talk about about vector calculation. So assume we have 2 points, point A and point A with xa, ya, z, a and a B point with its axis. So then the vector AB vector will be calculated as like xb minus xa and yb minus ya, zb minus za, and each direction will be addressed by a positive or negative of the subtraction between the value pairs of x, y, z. So after we get the AB vector, we can count the distance, or you can say length, of AB vector, a vector, by count its determinant. So the determinant formula is look like this part, and it will be computed by the n square root of the sum until the n dimensions are reached. So we generate the step size means like by multiple a random number from 0.5 to 1. It means like every step length you walk and generate visual radius toward the global hotspot. It means like in your visual site or a circle of your visual. And another one is a local hotspot to a local hotspot, and it's still a visual radius. And as we mentioned, we compute a velocity for extrovert because the extrovert's behavior is different from introvert. So we have to show different kinds of, and the introvert will talk about in next slide. So on the right side we can see the local hotspot and global hotspot, and we will design moving direction by random number, but it include where the global and where the local, and we vary direction. Then we talk about introvert, as we supposed to make the introvert people will leave the hotspot as much as they can. So we use negative random number and to times our vector to increase an axiom vector that looks like leave the hotspot, the global and the local, and it also vary directions like the extroverts do. And the third situation is someone get drunk, and this is like a special situation is they get drunk, and we know this is a belongs mark, and the other mark is means reduction and except, and it means potential state for all locations within visual except the place he visited before, because MEM means memory. So we have another place to record what the place he have gone, so he won't go back again. So it's like the right side is a red circle, so it's like the last point he go, so he won't go back. After we talk about extrovert, introvert, and drunkard, we show the update participant velocity weight like PSO, and we update the participant location for the extrovert and introvert. And for a drunk participant location, we have a random way limit in the drunk vision domain, because if you get drunk, your path will be like a random in our assumption. So with n dimensions and distance between his current location X and a global hotspot means his visual site for a drunkard. And here is our practical example. So we choose a maximize problem like this one, and yeah, we just do some practical example for this. And for iteration 1, there is a type, so we will decide how many extrovert and introvert in the party, and in the first iteration everyone won't drunk. And also in our pseudocode we do in the first in every iteration we decide who is drunker at the last part. So it's kind of close to PSO, and we create the population and we set the max step size and keep going. And because this is the first iteration, we copy local hotspot to the population, and you can see a memory for the first and the second variable is 0. It means like because it's first iteration we don't have the information before, so it keeps 0. And after we compare to each particle's fitness, we found that the second one in this practice is the second one is have the biggest fitness value. So we decided as a global hotspot position, and we save it. Yes, okay. So we copy to the global. So in the first iteration, the global hotspot is the second one, and we record in it. So we can see the minus calculate from the radius toward the global hotspot and local hotspot. It looks like xg vector and xm vector. Yes, so because so we just minus it, and doing the minus, the result can show in the new forum as we see in the below. In the bottom side of the slide, so we can count. It shows the distance toward global hotspot, and it actually vector toward the local and the global hotspot. So after we have xg and xm vector, we can generate xm vector exact to decide the length of the next step. Because the first particle is extrovert, so we count it as an extrovert weight, like, and the result is show like blue number. And after we count xm vector, we can fill into forum, and when count the action vector, we have to know what is the particle's type, because the extrovert and introvert have different behavior. So you have different way to count action vector. We know what is action vector is, then we can count the delta V. So action vector is like a length of the vector, and we add a vary direction on it. It's step function times a random number and time determinant of vector action. So the change of the velocity for the first particle is shows like 0.29 and 0.571. Thus, we will know how many value we will change our velocity. By the delta V, we can get the new velocity for the iteration 2, and shows below is like after the new velocity is 0.561 and 0.953, and the others particle will upgrade like this. So we get the velocity of iteration 2, then we can add on the position in iteration 1, and we will get the new position. So after we add it, it gets like a new one. So we have to compare the fitness between the former iteration, the iteration 1 and iteration 2, to see if it goes to the better place. So first we should memory the point we have gone. So we will want back as our assumption. And the second is to compare to the fitness in between iteration 1 and iteration 2. So we see in the first or for the first particle, the iteration 2 shows better, but the second particle, it doesn't shows better, so we keep it. And the third shows better, so we change the local to the second iteration's position. So it's like what we do in the PSO. And after comparison, we see in the second iteration 2, it has a higher fitness value is 32.694. So we change to, so it's local, it has the best local, so we change to the global hotspot position. And close to the end of our algorithm for one iteration, we randomly create drunker. So if it drunk, we will have another behavior to do a position. So it's like a pseudocode. So if it drunk, you will find a global hotspot or drink for X iteration, so you will be in stop. And it helps us to find the random. other because random, maybe you will find a better fitness value. So what is next? Means what we need to do is code in Python and verify algorithm performance and add modification to improve performance. That's what we going to try. And it's QA, but I don't think we have QA because the remote, but you still can access. And thanks for listening. Thank you guys.